In this video, we continue our discussion of infinite series. In particular, we look at the nth term divergence test, often called simply the divergence test. So before we actually talk about the nth term divergence test, I just want to take a broader look at series, infinite series, and discuss that question, what is it that makes a series converge, or what is it that makes a series diverge? So below you'll see 4 examples, A, B, C, and D. Let's take a moment now and look at each of these and talk about them individually. In the first infinite series, we have the series 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus etc., etc., etc. Your first instinct, does this series diverge? Does it grow infinitely big? Or does it converge? I think you probably agree with me that this series should be something that we consider to be a diverging series. I think you would say that this series diverges. Why would you say that? Because this series, first of all, the terms, they just seem to be getting bigger and bigger and bigger, right? They're just growing infinitely larger. And so if I add a bigger number to my previous number, and then I add another bigger number to my previous number, well, it just seems that this sum is going to go to infinity. I mean, that makes logical sense. So that first series diverges. Now, what about that second series? 1/2 plus 1/2 plus 1/2 plus 1/2 plus 1/2 plus ... Now, our terms in the series are not getting bigger. In fact, it's always constant, right? So we keep adding a constant number as we go on. The sequence 1/2, comma 1/2, comma 1/2, comma 1/2, that sequence converges. That converges to the value 1/2. That means that I know that that number in that sequence is 1/2. But the sum is different, right? When we're looking at a sum, we're looking at adding numbers. So 1/2 plus 1/2 is 1. And then I add to it another half, so that's 1.5. And then I add to it another half, and so that's going to give me 2. And then I add to it another half, and I'm going to get 2.5. What is happening as I look at the partial sums for this series? As this series keeps adding a half, what's happening to the value of that sum or that partial sum? It's just growing infinitely large, correct? Right? These guys are growing. The sums, the partial sums are growing. And if the partial sums are growing infinitely large, because I keep adding a constant number here, that means that this whole series also is going to have to diverge, right? Because I keep adding a half forever and ever and ever. This sum will never stop. It will never converge. This is also going to diverge. This series diverges to infinity. All right, example C. So far, so good, right? Okay, example C. 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus ... This time, our terms are doing what? They're getting smaller. Each time, I'm adding a smaller term. In fact, the next term I would add in this series would be 1/6, and then 1/7. So my terms are growing smaller, right? So the terms are growing smaller. But the question is, are they growing small enough, fast enough? Does this series look familiar? We actually talked about this in a previous video. This is what we call our harmonic series. And do you remember what we said about the harmonic series? The harmonic series diverges. So even though the terms are getting smaller, in fact, those terms are heading to 0, correct? Even though they're getting smaller and heading to 0, they're not getting smaller fast enough. The harmonic series diverges. And we're actually going to talk about that in the next video. Well, not this next video, but when we start talking about the integral technique, we're actually going to prove this. So hold on till then and we'll actually discover why it diverges. But this series also diverges. Okay, so how about that last example? Let's consider the series 1 plus a half plus a fourth plus an eighth plus 1/16. I don't know if you recognize this series, but first of all, let's talk about it. Our terms are getting smaller, just like in the previous example, C. The terms are getting smaller. In fact, they're heading to 0. What would be the next term in this series? After 1/16, it would be 1 over 32. And then the next guy would be 1 over 64. How am I getting those terms in that series? I'm noticing that each term comes from its previous term, and each time we're multiplying by 1/2, right? This is an example of a geometric series. We just got done talking about geometric series, right? And this particular geometric series, our R value, the thing that multiplies each term, is 1/2, and because 1/2 was less than 1, it meant that this series converges, right? So the terms are getting smaller, they're heading to 0, and on top of that, they're getting small enough fast enough. Because of that, this series converges. Now, we could go through and get the sum. We know how to do that. Its sum is A over 1 minus R. But right now, my focus is just looking at what is it that makes a series converge versus diverge. The first condition, of course, is that the terms have to be smaller. They have to be heading to 0, but that's not enough. This idea, though, allows us to talk about what the next test is for series. Maybe we can't decide what happens when our series head to 0 at first look, but we can definitely state something. If our terms aren't growing smaller, if they're not heading to 0, well, that definitely means that we're going to be diverging, right? If your terms aren't heading to 0, then your series obviously are diverging. It's a simple fact. And in fact, that's the basis for the divergence test. The divergence test states, if the limit as n goes to infinity of the nth term of a series is equal to some finite number c, that's not 0. So c can either be a finite number that's not 0, or the limit doesn't exist, and that also includes infinity or negative infinity. So if you have a limit that is infinity, negative infinity, does not exist, or is some finite number that's not 0, then the series diverges. Those terms have to be heading to 0 for your series to converge. So if those terms are not heading to 0, that means that your series diverges. I do want to point out that extra condition, though, that we mentioned. You can have terms going to 0, like in our harmonic series, and that still diverges. So if the terms are heading to 0, the divergence test does not tell us automatically that the series is converging. All the divergence test allows us to do is tell whether a series diverges or not. But this is powerful in many aspects, and it helps us narrow down right away series that automatically we don't even want to mess around with. We know that diverge automatically. When we apply the divergence test, if we get a limit that is not 0, does not exist, is infinity or negative infinity, then we simply can state by the divergence test the series diverges. However, if we use the divergence test and discover that the terms actually go to 0, well, then the test is said to be inconclusive because we're not sure yet whether it's going to converge or diverge. We leave that up to other tests. All right, so let's take a look at one quick example first of the nth term divergence test. Example 1. Apply thy divergence test to the following series and then state our conclusion and result. We have the infinite series n equals 1 to infinity of the natural log of 3n over 4n plus 1. So let's write down that series first of all, so I know where I'm starting. N equals 1 to infinity of the natural log of 3n over 4n plus 1. Now I want to apply the nth term divergence test. And in the nth term divergence test, it's actually a very quick test. I don't have to look at partial sums. I don't have to do anything except look at the nth term of this series, which is the natural log of 3n over 4n plus 1, and ask the question, what is that limit? If that limit is not 0, automatically the series diverges. So let's see, what is the limit as n goes to, infinity of the natural log of 3n over 4n plus 1? What is the limit as n goes to infinity of the natural log of 3n over 4n plus 1? So from a discussion in Calculus 1, you recall that we can actually take the limit and put it inside the natural log if we want to make it a little easier in looking at this, mainly because natural logs are scary things, right? But if we want, we can put the limit inside our natural log. It's a continuous function. All is good there. So now let's take a deeper look. So really, we're just asking ourselves, what is the limit as n goes to infinity of 3n over 4n plus 1? That's like infinity over infinity at first glance, right? The top would go to infinity, the bottom would go to infinity. It's a good candidate for L'Hopital's rule if we wanted to. Or simply, the way that I've been looking at them is that when you have a polynomial over a polynomial, recall, only the highest degree terms are what really matter. Those are the only things that are getting affected when you're taking a limit as n goes to infinity. So as n goes to infinity, really, the only thing I'm really worried about is the highest degree on the top polynomial and the highest degree on the bottom. Again, because as you go to infinity, all the other terms are insignificant in polynomials. So if I have 3n over 4n, that's actually just 3/4, right? And so we are looking at the natural log of the limit as n goes to infinity of just 3/4 after a quick cancellation. And that's just 3/4, right? So it looks to me like the limit as n goes to infinity of 3n over 4n plus 1 is just the natural log of 3/4. Now, how does that help us? Well, that's where the divergence test comes in, right? Because this is not 0. The nth term divergence test tells us that this series automatically diverges. Automatically. So let's state our conclusion. By the nth term divergence test, or by the divergence test, we see that the limit as n goes to infinity of our nth term equals the natural log of 3/4, which is not 0. Thus, the series diverges. I like the nth term divergence test. It's a quick test, and right away it tells us if something diverges. And if it does, then we don't even have to worry about considering its convergence. In the next video, we look at a couple more examples where we apply the divergence test.